Okay, so we want to carry our discussion about central forces, and the first thing we want to understand is what is the central force. Okay, and we have looked at a lot of central forces already. Right, gravitational force is also a central force. Okay, and it is defined as any force that acts between two bodies, and this force is directed along the line between these two bodies. Okay, and one of the main reasons why we are interested in central forces in our study discussion in mechanics course this semester is that we want to look at this two body problem where you have situations like planetary motion, you have for example nuclear forces, you have the hydrogen atom in which you have the nucleus and one electron going around. So all these are kind of a two body problem, and what we'll try to do is we'll try to use this central force concept and reduce this two body problem into a one body problem, and then get some solutions and get some intuition of the problem at hand, and how we can use our physics to solve and predict some of the properties. Okay, so again it's a force that is acting between two bodies, and it is directed along the line between them. And additionally, what you should also remember is that the magnitude of this force will depend on the radial coordinate r. Okay, so again, not to confuse ourselves, we just are saying that there are two bodies here. Okay, and what we are saying is the central force is the force that is acting along the line that is connecting these two bodies. Okay, so it's not acting along, a force is not acting along such way, right? So that is not the case. It is directly along the line between them. Okay, and this separation distance r, okay, that is the value on which this force is dependent. So we have looked at that before. The force that suppose object 1 is exerting on 2, right, with some value f of r, and it is directed along the unit vector r cap. Okay, so that is how we define a central force. Okay, and then all the other things will come into picture. We know f is equal to ma, we can use that relationship, and again a is again mr double dot, where r double dot is just d square r by dt square. Okay, so that is just acceleration. Okay, so by definition. So let's look at this problem in terms of spherical coordinates. So if I look at my origin here and I want to define any point P here, which is at a distance r. Okay, and now the what I'm saying is I'm looking at a problem where my origin is defined, and let's say there is a body that is doing some kind of motion, like say like a circular motion like this. Right, we have looked at this motion before in satellites and in planets, and then we had defined this r. And if I take this problem to spherical coordinates, then I have to define my values of theta and phi, and then I can write my spherical coordinates x equals to r sine theta cos phi, y is equal to r sine theta sine phi, and z is just r cos theta. Okay, so those are just my xyz coordinates in my spherical coordinates. Okay, so you should be familiar with these. So the gradient, divergence, and curl, when you look at the spherical coordinates, these are the formulations. Okay, so basically, for example, let's just take the curl of a function. So let's say curl of a function u will be given by this r cap, unit vector r, 1 by r sine theta, and partial derivative with respect to theta, and then you have the same function phi in terms of sine theta. Okay, and then you have partial derivative of the same function in terms of phi. Okay, so that is just one term, and then you have a theta cap term and you have a phi cap term. So this entire thing is your curl of a function in spherical coordinates. Okay, so this is something you'll be using a lot later on in electricity and magnetism as well. Okay, now if you look at this spherical coordinates, there are 6 terms here. Okay, however, what happens is we know that suppose I'm looking at the conservative force. Okay, and central forces are conservative. Okay, that is very important. So what does that mean? That means that del cross F, for where F is a central force, will be equal to 0. Okay, that means whatever my function here is, if I take the curl of that function in spherical coordinates, my answer should come out to be 0. Okay, and what it means is, if you look at this entire function here, okay, and you try to solve it out, we know that we are taking curl of this F. F is what? F is only dependent on your r, so there is no dependence on your theta and phi. So what happens is, your r, when you take curl of this function, you're taking curl of some function here which is also dependent on r, so r cross r will become 0. So this entire term in the denominator here, this term will become 0. Okay, so you are left with only these two terms. So you're left with one theta cap term, and you're left with this first term right here. Okay, because again this is something that is dependent on r, so that will be 0, and similarly this is dependent on r, so that will be 0. So all you're left with one term here, theta cap 1 by r times this term here, and you're left with phi cap 1 by r, and then you're left with this term here. Okay, so those are the only two terms that are left. Okay, and from here, if this and this term, when they subtract, they have to be equal to 0, because that is what defines as a conservative force. Then you know that your force F has to be independent of theta and phi as well. Okay, so that's how you know that everything is fine and dandy. Additionally, this is about the force. If you're looking at potential, what is potential? Potential is this function right here. We know gradient of the force is your potential energy function. We have looked at that, right? Force is negative of the gradient. So if you look at this term, this is what will give you the potential. Okay, so the potential will come from here. All right, and again from here, if you look at the potential, you're taking some partial derivative of F. Now F here, this function will be your potential V. Okay, so you get r cap dv by dr, and you get 1 by r dv by d theta, and you get 1 by r sin theta dv by df. Okay, d phi, sorry. So, and so again here, if you look at this, your dependency in terms of theta and phi again goes to 0, because this function v is just a function of r, so the partial derivatives here will go to 0. So you will only be left with a term that is dv by dr r cap. So again the potential will only depend on the r function. Okay, so that's just the basic definition of the force. Okay, what we are looking after is much more application based, and mainly what we are trying to do is we are trying to now take this problem that we had discussed earlier about just we had looked at the origin, and we said let's take one object going around in orbit, and then we can have the centripetal force and all that stuff we have done before when we looked at satellites. Now we are saying that we will not keep that origin as one of the objects. Okay, like Earth is not going to be on the origin. Okay, so though both of these objects can move per se, there is no limit on them. So then essentially it is a two body problem, whether m2 is oscillating and or orbiting around m1, or m1 is orbiting around m2. We don't care. It is just a force that is existing between these two objects. Okay, now that is a general three-dimensional problem. Okay, and we have two bodies that are interacting, and there are some forces at play. So now again, if I'm trying to define the position of each of these objects like I'm doing in spherical coordinates, again I will have 1 2 3 dimensions for one of the objects, and then again I'll have 1 2 3 dimensions for the second object. So then I have 6 parameters that are describing the position of these two masses. Okay, so then it becomes very complicated problem. Okay, now what I want to do is I want to take this two body problem and reduce it to one body problem, and then it will simplify the picture a little bit further. Okay, so there is a specific strategy to do that. Okay, so let's just define what is going on here in the first place. All right, we have two masses m1 and m2. Okay, and of course the force of interaction is along this line, okay, where it is given by this r cap, the unit vector. Okay, r1 and r2 are the position vectors, okay, of m1 and m2. Okay, and by definition you can see what is going on here. This r vector, which is this capital vector r, is just your r1 minus r2. Okay, so you can just clearly see this relationship from here, because you have one vector here, r2 plus r will be equal to r1. Okay, so then r will be r1 minus r2. Okay, so now we are defining this position vector r, which is the separation vector between these two vectors, in terms of r1 and r2. Okay, so that is what it is. And then this force that is acting along this line, okay, that we can define as f, right? And f will be some vector f times r. Okay, so we are saying that this depends only on r. Okay, and of course there is a r cap here. Okay, so we don't want to forget that there is a r cap that defines the direction along which the force is acting. Okay, now we have already discussed this. It's a conservative force, so then we can talk about potential energy. The potential energy term will be minus do by dr, r cap. Okay, and additionally, now what we are going to do is to reduce it to a one body problem. Instead of just looking at the two masses and the position vectors, what we are going to do is we are going to use the center of mass coordinate system. Okay, now if you remember from our unit 2, the center of mass, the position, was defined as m1 r1 plus m2 r2 divided by the total mass, right? So this was a formula of how we can define a center of mass position. Okay, so we had done this for individual point particles. Okay, so here you have now considered point particles, right? And r is going to be some position of center of mass along this line. There is going to be somewhere, there will is going to be a position of center of mass, right? If m1 and m2 are the same, the position of center of mass is going to be in the center. If its m1 is higher in mass, then it is going to be along this, closer to the m1 point. Okay, so we had done those problems before. So we are again trying to say that we are going to apply the same idea, and we are going to use the idea of the reduced mass, which is given by this factor mu. Okay, so let's see where all of this is coming from. Okay, so again, let's say this is the center of the mass. Okay, now I am defining this capital R as my coordinate system of from the origin of the position to the center of mass. Okay, which is defined here as capital R, and this is the formula m1 r1 plus m2 r2, and capital M is now the total mass, which we can just define so that we don't have any issues where it is coming from. It is just m1 plus m2. Okay, now let's see how we can simplify this picture using our Newton's laws. Okay, now if I have two objects, okay, and what I can say is the force F1 on 2, for example, will be some force F of R, and that depends on some unit vector R. Okay. Similarly, then just by the Newton's third law, we know that F21 will be equal and opposite force, so we can define it as minus F of R for R cap. Okay, and now what we can do is we can use the MA relationship, the Newton's second law. So for the first force m1 d square r1 by dt square, okay, is equal to f12. Okay, and similarly from here we can say that d square r1 by dt square is equal to 1 by m1 times f12. Okay, now for the second object, we can write m2 d square r2 by dt square is equal to f21. Okay, so these are the equations of motion for m1 and m2. Okay, and from here I can say that d square r2 by dt square is equal to 1 over m2 times f21. Okay, so now I can subtract these two equations. So if I do that, I get d square r1 by dt square minus d square r2 by dt square. Okay, so I'm just subtracting this, so I should get 1 by m2 I can actually further simplify this, right? So I have 1 by m1, right? And this is f of r, right, times r cap. And here I have 1 by m2, and this is minus f of r and r cap, right? Just by the definition from here, 1 and 2. All right. So now when I take a subtract sign here, right, minus of d square r2, then minus and minus will cancel. Okay. So what I'm left with is I get 1 by m1 f of r cap minus of minus 1 by m2. Okay. F of r cap. Okay. So this minus and minus sign will cancel. Okay. Now let's see. So now I have a common double derivative, so I can take that out. So I can say d square by dt square r1 minus r2. This is the same as writing it here. When I take the derivative inside, is equal to f of r is common, and I can just take that outside. R cap is also common, and then I get 1 by m1 plus 1 by m2. Okay. So again, it's just a little bit of trick with the math. All right. So let's write what equation we have gotten so far. We got d square by dt square r1 minus r2, okay, is equal to 1 by m1 plus 1 by m2, okay, f of r times r cap. Okay. Now 1 by m1 and 1 by m2 is what? So we can just take the LCM. So it is m1 plus m2 divided by m1 m2. Okay. And I have f of r on r cap, and I have d square by dt square r1 minus r2. Okay. So remember, r1 minus r2 in our problem, we have defined it as r vector r. Okay, that is the position vector r between m1 and m2. Okay, so this I can write on the left hand side as d square by dt square of r. Okay, and this m1 by m2, m1 plus m2, the total mass divided by m1 m2, what I can do is I can write it as a factor which is called the reduced mass. Okay, and then my equation will become like this, where mu is reduced mass, and it is given by 1 by m1 plus 1 by m2. Okay, and see, why is it called reduced mass? If you look at this term here, suppose m1 was equal to m2, what do I get? If m1 is equal to m2, my u becomes I get 2m1 in the numerator, right, and I get m1 square in the denominator, because m1 is equal to m2. Okay, so that would cut this, and I get 2 by m1. Okay, so again, it is lower than individual masses of m1 and m2. Okay, so we have to be careful of why we are calling it reduced mass. All right. So anyways, the final relationship that you're getting here is of what kind, right? So you have your relationship of I think we have to define it as 1 over mu. Okay, 1 over mu is what I'm going to define here as my reduced mass. Okay, and then I will get uh, mu times t square r by dt square is equal to f of r and r cap. Now I am happy with the relationship. You see, now what I'm seeing is that force is equal to some mass times acceleration. Okay, so now I have reduced the two body problem into a one body problem, where I just have an equation which says force is m times a, and mass is not just any mass, it is a reduced mass, which is this mu. Okay, and we have to be careful. We are defining 1 over mu as 1 over m1 plus 1 over m2, but mu is what is called as reduced mass. Okay, so not 1 over mu is reduced mass, mu is reduced mass, but the factor 1 over mu is this factor 1 by m1 plus 1 by m2. Okay, and then you get the right relationship. Force is equal to m times a. Okay, and now instead of looking at these individual bodies, what you're looking at is you're looking at the motion of the center of mass. Okay, that's all we have done. and we have simplified the problem of these two objects that are doing some complicated motion uh, that is very hard to predict mathematically and understand in physics, rather to convert them into a simple one body problem, okay, which is just force is equal to ma. So you have a mass term, so you have an acceleration term. All you have to do is you have to look at the coordinate r, and the problem will be much more simplified. Okay, so you can also say that this entire system, which was consisting of two objects that was exerting forces on each other, has now been reduced to a system that behaves like a single particle of mass mu. Okay, and uh, the point where the force is acting is your position on the center of mass. That is the point where the force will be acting for this collective system. I have some examples here where you have not two objects but three objects. Okay, now they are constantly exerting force on each other. Okay, and look at the complicated motion they are doing. Okay, and this motion of where these objects are going to be at some position at some certain time is very difficult to predict. Okay, it looks very complicated, you see. So in scenarios like this, it is very difficult to take each of individual particle and describe how it is moving. Rather, it is much easier if you look at the center of mass. For example, in the bottom problem here, the center of mass of all these three particles that are exerting forces on each other is always fixed. So you see how easy and simplified the motion of the center of mass is. It is not moving at all. Okay, so if I am at another planetary system very far away from these three objects that are doing some kind of motion, I can just consider all of these three particles to be at this center of mass position, and I can take the reduced mass of these three particles at this position, and I can do a calculation figuring out what are the forces that are being exerting from this system to some other system. You see, and same idea goes for other problems like these as well, where you have this gravitational force acting between these three particles. You see, right? So again, a lot of complicated motions that they are doing. All right, and the motion is happening. Why? Because of the interaction between the particles. Remember, when we were talking about Earth going around the sun, the motion is happening. Why? Because there is gravitational force of interaction between the two objects. Okay, and that has to be taken into consideration. So the forces that are acting between these two particles, that is the interaction that is making the motion happen the way it happens. Okay, and of course some of these problems are hard to predict, and one of the way to simplify the picture is to just look at what the center of mass is doing. Okay, and that's the whole idea. Okay, that's the whole idea that we want to get after. Okay. Okay, so let's look at one of the applications of this two body to one body problem, and that is for the hydrogen atom. Okay, and the idea is the same. You have the nucleus, you have some electron that is going around the nucleus, and then it's a two body problem. Okay, let me just draw it to scale. There it is, right? So now I'm considering these two bodies, which is a positively charged here nucleus and the electron here that is going around, and then this two body problem I can reduce to a single body problem. How? I have just to take this reduced mass of the system, and I can say, let me take the mass of the proton and the mass of the electron into the consideration. Okay, and then I have the mass of the proton plus mass of the electron. Okay, so that is my reduced mass of this hydrogen atom. Okay, and from here what I can do is I can take your one of the masses outside. Okay, let's say what is the mass of the electron? Can anybody tell me? And mass of the proton?
0.67 into 10 to the power minus 27.
You see, in this scenario, what is happening? The mass of the electron is much smaller than the mass of the proton. Roughly, mass of the proton is about 1836 times mass of the electron. Okay, so now what I can do is I can take this result here. Okay, and I can do some fancy mathematics. I can take the mass of the electron outside, okay, and what I can do is, if I do that, I am left with uh, mass of the proton divided by mass of the proton plus mass of the electron, okay, and this I can also write as 1 divided by 1 plus me by mp. Okay, so I've just taken the numerator in the denominator. Okay, now here I know that me by m of p is going to be a very small number. Okay, because mass of the proton is very high, and we have done the Taylor series expansion. In that case, 1 by me plus np raised to minus 1, okay, will be 1 minus me by mp. Okay, that's a rough calculation. Okay, so in that case, this entire second term here will just become reduced to this term. So I get mu is equal to me 1 minus me by mp. Okay, and now again I can say that me by mp is a very small number. Okay, so you can see it's like about 0.00 something, so it doesn't have much effect on the system. Okay, so to a rough approximation, I can just take mass of the electron to be the reduced mass of this entire system. Okay, because this factor here is about 0.001, so it will hardly affect my value of mass of the electron. Okay, so when I look at the hydrogen system, okay, I can just simplify the picture and just say that it's a system of reduced mass of having just the mass of the electron. Okay, and in this example now, what we are going to do is we are going to consider gravitational force. Okay, so we know the force we have defined is some value of magnitude f of r, and it depends, and it's directed along the line, so r cap. So when we consider gravity, so this force we know is g m1 m2 divided by r square and the unit vector. Okay, and to reduce the two body problem into one body problem, what we have to do is we have to take the reduced mass of the system, right, and then we have d square r by dt square. Okay, so that is the scenario. Okay, so I can equate these two equations. Okay, and if I do that, basically what am I getting? I'm getting u d square r by dt square is equal to minus g m1 m2 by r square r cap. Okay, and from here I can say that t square r by dt square will be 1 over mu, and then I have minus sign is there, and then I have g m1 m2 divided by r square. Okay, and what is mu? Or let me say, what is 1 over mu? Remember 1 over m1 plus 1 over m2, that is the reduced mass. So from here, if I solve this, I was getting m1 plus m2 divided by m1 m2, right? Or mu is nothing but the inverse of that. So m1 m2 divided by m1 plus m2, right? So that is what I'll get. So to reduce this expression, I will get d square r by dt square will be minus 1 over mu is m1 m2 divided by, so I can take it in the numerator m1 plus m2, and then I have a g and m1 m2, and I have divided by r square. Okay, so now I'm getting some cancellations, m1 m2 and m1 m2 get cancelled, and I get minus g m1 plus m2 r by r square. Okay, so you see now our relationship becomes the acceleration, right, is this value right here, minus g m1 m2 by r square. Okay, so again, what is this expression telling me? So it is telling me that here the mass, because ma is going to be the force, so it's telling me that this is nothing but um, the acceleration that a unit mass is experiencing. Okay, because ma, if I put ma here, then that is going to be my value of the force. Okay, and if I take m as 1, then that is what this expression is. So for a unit mass, the acceleration that it will feel is going to be this term right here, minus g m1 plus m2 divided by r square. We can think of it in other terms as well, right? That it is a force that is being experienced by a unit mass. And what is exerting the force? The force is being exerted by the total mass of the system, m1 plus m2. Okay, so there are two ways you can think about it. Okay, and of course the distance between them is going to be r. Okay, so that's how we have reduced the two body problem into a single body problem. You see, so now you're taking the entire system to have the total mass, and that is entire system is extending a force to a unit mass. And then you know that a unit mass is our test mass. So whatever we put there at that location, it's going to experience that much amount of force. Okay, so if you put 10 kilograms, it is going to experience some force. If you put 100 kilograms, it is going to experience some other force. Remember, so for our generic purpose, we consider unit mass to be at the location where we want to see what is the gravitational force of the field that is exerting at that position. Remember, that was the whole idea of calculating what is the gravitational field or gravitational force or potential exerted by objects. So it's the same idea here. So the force that is being exerted by the total mass of the system, okay, at a distance r to a unit mass that might be located at that certain position if we keep a unit mass at that position. And we can again, you see, this same kind of idea can be applied to a satellite as well. So now we have a satellite that is going around the earth. Okay, and the satellite has some mass, okay, m1, and the earth has some mass m2. Okay, so when you look at this entire system of what this entire system is going to do, all you have to do is you have to plug in that both the uh, masses in here. So you'll have the total mass of the satellite and the earth, and they are going to exert some force onto some other object. And you know, so now we have taken the collective system, and from that collective system we can figure out other things as well as to what is going to be the angular velocity and all this stuff of the satellite and so on. Okay,